Yes, the service point or the load end of the service lateral is located on the primary side of the outdoor transformer. That's correct. According to National Electrical Code Section 250.24 AN, the grounding electrode conductor, referred to as GEC connection, can indeed be made anywhere between the service point and the service disconnect, and this includes the secondary side of the outdoor transformer. If you choose to make the GEC connection at the secondary of the transformer, as permitted by Section 250.24 AN, you are not required to install another GEC connection either outside or at the transformer per Section 250.24 ATWR. Section 250.24 ATWR mandates an additional grounding connection to a grounding electrode at the transformer, specifically when the transformer providing the service is situated outside the building and the initial GEC connection has not been established at the transformer's secondary location. In essence, the code provides flexibility in locating the GEC connection, allowing it either at the service disconnect or at the transformer's secondary. However, the requirement for an additional grounding connection at the transformer only applies when the GEC connection is not made at the transformer's secondary side and the transformer is located outside the building. It is important to understand the roles of the grounding electrode conductor and the grounding electrode. The grounding electrode conductor connects the system grounded conductor, often the neutral, to the grounding electrode. The grounding electrode is a metallic object buried in the earth, providing a physical connection to the ground. Common grounding electrodes include metal underground water pipes, metal frames of buildings, concrete encased electrodes, and ground rings. The size of the grounding electrode conductor is determined by National Electrical Code Table 250.66 based on the size of the service entrance conductors. Proper grounding and bonding are essential for electrical safety. Grounding provides a low impedance path for fault current to return to the source, allowing overcurrent protection devices, such as circuit breakers or fuses, to quickly clear the fault. Bonding ensures that all metallic parts of an electrical system are at the same electrical potential, minimizing the risk of electric shock. The National Electrical Code provides detailed requirements for grounding and bonding, and it's critical for electricians and electrical engineers to adhere to these requirements to ensure safety and proper system operation. Let's delve a little deeper into grounding electrode systems. A grounding electrode system may consist of multiple grounding electrodes that are bonded together. This enhances the effectiveness of the grounding system by providing multiple paths to ground. The most common grounding electrodes include a metal underground water pipe that is in direct contact with the earth for 10 feet or more, the metal frame of a building or structure that is effectively grounded, a concrete encased electrode consisting of at least 20 feet of bare copper conductor encased in concrete, and a ground ring consisting of at least 20 feet of bare copper conductor buried directly in the earth at a depth of at least 2.5 feet. The grounding electrode conductor must be connected to the grounding electrode system in a manner that ensures a permanent and effective ground path. This connection should be accessible for inspection and testing. When using a metal underground water pipe as a grounding electrode, it must be supplemented by an additional grounding electrode, such as a ground rod or ground ring. This is because metal water pipes can be subject to corrosion and may not provide a reliable long-term ground path. Ground rods must be at least 8 feet long and driven into the earth to a depth of at least 8 feet. Ground rings must be buried at a depth of at least 2.5 feet. The resistance of the grounding electrode system must be low enough to ensure that fault current can flow back to the source, allowing overcurrent protection devices to operate. In many cases, the National Electrical Code requires the resistance to ground to be 25 ohms or less. If the resistance is higher than 25 ohms, an additional grounding electrode must be installed. Regular inspection and testing of the grounding electrode system are essential to ensure its continued effectiveness. This includes visual inspection of the grounding electrode conductor and connections, as well as testing the resistance to ground. Any damaged or corroded components must be replaced immediately. Now let's clarify the distinction between grounding and bonding. Grounding refers to the connection of the electrical system to the earth, while bonding refers to the connection of metallic parts within the electrical system to create an electrically conductive path. The purpose of grounding is to provide a low impedance path for fault current to return to the source, while the purpose of bonding is to minimize voltage differences between metallic parts, reducing the risk of electric shock. Bonding is achieved by connecting metallic parts together using bonding jumpers or conductors. These bonding jumpers must be sized according to the National Electrical Code requirements. Common examples of bonding include bonding metal water pipes, gas pipes, and metal enclosures of electrical equipment. It's also essential to bond the metal equipment grounding conductors within a circuit to the metal enclosure of the electrical equipment. This ensures that if a fault occurs, the fault current will flow back to the source, tripping the overcurrent protection device. Proper grounding and bonding are critical for protecting people and property from electrical hazards. It's essential for all electrical work to be performed by qualified and licensed electricians who are familiar with the National Electrical Code requirements. Let's consider some additional points regarding grounding electrode conductor sizing and installation. The size of the grounding electrode conductor is determined by National Electrical Code Table 250.66, based on the size of the service entrance conductors. For example, if the service entrance conductors are 4/0 American wire gauge copper or 250 kc mil aluminum, the minimum size of the grounding electrode conductor is 2 American wire gauge copper or 4/0 American wire gauge aluminum. The grounding electrode conductor must be installed in a manner that protects it from physical damage. It can be installed in conduit or raceway, or it can be run exposed along the surface of a building. If it's run exposed, it must be securely fastened to the building structure. The grounding electrode conductor must be continuous from the service equipment to the grounding electrode. Splices are not permitted in the grounding electrode conductor, unless they are made using irreversible compression connectors or exothermic welding. The connection of the grounding electrode conductor to the grounding electrode must be made using listed connectors or clamps. These connectors must be suitable for the type of grounding electrode being used. For example, if you're connecting the grounding electrode conductor to a ground rod, you must use a listed ground rod clamp. The grounding electrode conductor must be connected to the grounded conductor, typically the neutral conductor, at the service equipment. This connection is typically made at the neutral busbar in the service panel. The grounded conductor must be insulated, except for the portion that is used for bonding to the service equipment enclosure. The insulation helps to prevent unintentional ground faults. In addition to the grounding electrode conductor, there is also an equipment grounding conductor. The equipment grounding conductor is used to ground the non-current carrying metal parts of electrical equipment, such as metal enclosures, conduit, and motor frames. The equipment grounding conductor provides a low impedance path for fault current to return to the source, allowing overcurrent protection devices to operate. The equipment grounding conductor must be sized according to National Electrical Code Table 250.122. Based on the size of the overcurrent protection device protecting the circuit. The equipment grounding conductor must be connected to the grounding electrode system at the service equipment. This connection ensures that all metal parts of the electrical system are at the same electrical potential, minimizing the risk of electric shock. When running branch circuits, the equipment grounding conductor must be run with the circuit conductors. This helps to ensure that there is a low impedance path for fault current to return to the source. The equipment grounding conductor can be a wire, a metal raceway, or a combination of both. If a wire is used, it must be green or green with a yellow stripe. If a metal raceway is used, it must be electrically continuous and securely connected to the equipment enclosures. Proper grounding and bonding are essential for electrical safety. They help to protect people and property from electrical hazards by providing a low impedance path for fault current to return to the source and by minimizing voltage differences between metallic parts. It's important for all electrical work to be performed by qualified and licensed electricians who are familiar with the National Electrical Code requirements. Let's expand upon the discussion of grounding electrode systems and touch upon some advanced concepts. One such concept is the use of impedance grounding. In some industrial and commercial applications, it is desirable to limit the amount of ground fault current that can flow in the event of a ground fault. This can be achieved by using an impedance grounding system. In an impedance grounding system, a resistor or reactor is inserted in the grounding path between the neutral point of the transformer or generator and the grounding electrode system. This impedance limits the amount of ground fault current that can flow, reducing the risk of damage to equipment and minimizing the potential for arc flash. There are several types of impedance grounding systems, including resistance grounding, reactance grounding, and high resistance grounding. Resistance grounding is the most common type of impedance grounding. In a resistance grounded system, a resistor is inserted in the grounding path. The size of the resistor is chosen to limit the ground fault current to a specific level. Reactance grounding is similar to resistance grounding, but a reactor is used instead of a resistor. A reactor is an inductor that opposes changes in current flow. High resistance grounding is a type of resistance grounding that uses a high-value resistor to limit the ground fault current to a very low level. High resistance grounding is often used in critical applications where even a small amount of ground fault current can cause problems. Another advanced concept is the use of isolated grounding. In some sensitive electronic equipment, it is desirable to isolate the equipment from the building grounding system. This can be achieved by using an isolated grounding system. In an isolated grounding system, a separate grounding conductor is run from the equipment to the grounding electrode system. This grounding conductor is insulated from the building grounding system, preventing noise and interference from the building grounding system from affecting the sensitive equipment. Isolated grounding systems are often used in hospitals, laboratories, and other facilities where sensitive electronic equipment is used. It is important to note that isolated grounding systems must be installed in accordance with the National Electrical Code requirements. The isolated grounding conductor must be run in the same raceway as the circuit conductors, and it must be connected to the grounding electrode system at the service equipment. In addition to these advanced concepts, there are also several other considerations when designing and installing grounding systems. These include the soil resistivity, the depth of the grounding electrodes, and the proximity of other underground utilities. Soil resistivity is a measure of how well the soil conducts electricity. Soil resistivity varies depending on the type of soil, the moisture content, and the temperature. In general, soils with high moisture content and high salt content have lower resistivity than dry, sandy soils. The depth of the grounding electrodes is also an important consideration. The deeper the grounding electrodes are buried, the lower the resistance to ground will be. The proximity of other underground utilities is another important consideration. Grounding electrodes should not be installed near underground gas pipelines or other flammable materials. Proper grounding and bonding are essential for electrical safety. They help to protect people and property from electrical hazards by providing a low impedance path for fault current to return to the source and by minimizing voltage differences between metallic parts. It's important for all electrical work to be performed by qualified and licensed electricians who are familiar with the National Electrical Code requirements. Furthermore, let's talk about some practical considerations when dealing with existing electrical systems and grounding. Often, electrical work involves modifying or extending existing systems. In these situations, it's crucial to assess the existing grounding system to ensure that it meets current National Electrical Code requirements and is adequate for the new loads being added. Firstly, a thorough visual inspection of the existing grounding electrode conductor, grounding electrodes, and bonding connections is necessary. Look for signs of corrosion, damage, or loose connections. Any deficiencies should be corrected immediately. Secondly, test the resistance to ground of the existing grounding electrode system. If the resistance exceeds 25 ohms, additional grounding electrodes should be installed to reduce the resistance. Thirdly, verify that all metal parts of the electrical system are properly bonded together. This includes metal conduits, enclosures, and equipment frames. Bonding jumpers should be installed where necessary to ensure electrical continuity. When adding new circuits, the equipment grounding conductor must be properly sized and connected to the existing grounding system. The size of the equipment grounding conductor must be based on the size of the overcurrent protection device protecting the circuit, as specified in National Electrical Code Table 250.122. When replacing electrical equipment, such as panel boards or transformers, the grounding system must be upgraded to meet current National Electrical Code requirements. This may involve replacing the grounding electrode conductor, adding additional grounding electrodes, or upgrading the bonding connections. It's also important to consider the impact of any changes to the electrical system on the overall grounding system. For example, if a new service is installed, the grounding electrode system for the new service must be bonded to the grounding electrode system for the existing service. This helps to ensure that all metal parts of the electrical system are at the same electrical potential. Proper grounding and bonding are essential for electrical safety, especially when working with existing electrical systems. It's important to take the time to assess the existing grounding system and make any necessary upgrades to ensure that it meets current National Electrical Code requirements and is adequate for the new loads being added. Remember that unqualified individuals should never attempt to work on electrical systems. Always hire a qualified and licensed electrician to perform electrical work. Staying informed about the latest version of the National Electrical Code is also crucial for anyone involved in electrical work. The National Electrical Code is updated every 3 years, and it's important to be aware of any changes that may affect your work. Continuing education courses and seminars are available to help electricians stay up to date on the latest National Electrical Code requirements. By staying informed and following proper procedures, you can help to ensure the safety of yourself and others when working with electrical systems. Let's further elaborate on specific scenarios and applications related to grounding electrode conductor connections in the National Electrical Code. Consider a situation where you have multiple buildings or structures supplied from a single service. In this case, each building or structure must have its own grounding electrode system unless certain conditions are met. According to National Electrical Code Section 250.32, if the buildings or structures are supplied by a feeder or branch circuit, and an equipment grounding conductor is run with the circuit conductors, a grounding electrode system is not required at the separate building or structure. However, if a grounding electrode system is installed at the separate building or structure, it must be bonded to the equipment grounding conductor. This bonding helps to ensure that all metal parts of the electrical system are at the same electrical potential. Another common scenario involves the use of generators. When a generator is used as a standby power source, it must be properly grounded and bonded. If the generator is a separately derived system, meaning that it does not share neutral with the normal power source, it must have its own grounding electrode system. The grounding electrode system for the generator must be installed in accordance with National Electrical Code Section 250.30. If the generator is not a separately derived system, it must be connected to the grounding electrode system of the normal power source. This connection is typically made at the transfer switch. In addition to these scenarios, there are also specific grounding requirements for certain types of equipment, such as swimming pools, spas, and hot tubs. These requirements are outlined in National Electrical Code Article 680. Swimming pools, spas, and hot tubs are considered to be high-risk areas for electrical shock, so it's important to follow the grounding requirements carefully. The National Electrical Code also contains specific grounding requirements for sensitive electronic equipment, such as computers and medical equipment. These requirements are designed to minimize noise and interference and to protect the equipment from damage due to voltage surges. Proper grounding and bonding are essential for electrical safety in all types of electrical systems. By following the National Electrical Code requirements, you can help to protect people and property from electrical hazards. Always consult the latest edition of the National Electrical Code and seek the advice of a qualified and licensed electrician when designing or installing electrical systems. Let's discuss surge protection and its relationship to grounding. Surge protective devices, often abbreviated as SPD, are designed to protect electrical equipment from voltage surges caused by lightning, utility switching, and other transient events. SPD work by diverting surge current to ground. thereby limiting the voltage across the protected equipment. A properly installed grounding system is essential for the effective operation of surge protective devices. The SBD must be connected to a low impedance ground path to allow the surge current to flow safely to ground. The grounding conductor connecting the SBD to the grounding electrode system should be as short and straight as possible to minimize impedance. In addition to the grounding conductor, the bonding connections between the SBD and the protected equipment are also important. These bonding connections should be short and direct to minimize voltage differences between the equipment and the SBD. There are several types of SBD available, including Type 1, Type 2, and Type 3 SBD. Type 1 SBD are installed at the service entrance and are designed to protect the entire electrical system from voltage surges. Type 2 SBD are installed at panel boards and are designed to protect branch circuits from voltage surges. Type 3 SBD are installed at the point of use and are designed to protect individual pieces of equipment from voltage surges. The National Electrical Code contains specific requirements for the installation of surge protective devices. These requirements are outlined in Article 285. The National Electrical Code requires that SBD be installed in accordance with the manufacturer's instructions. It also requires that SBD be properly grounded and bonded. Surge protection is an important part of a comprehensive electrical safety plan. By installing surge protective devices and ensuring that they are properly grounded and bonded, you can help to protect your electrical equipment from damage due to voltage surges. Remember to consult with a qualified and licensed electrician to determine the appropriate type and location of SBD for your electrical system. They can assess your specific needs and ensure that the SBD are installed in accordance with the National Electrical Code requirements. Moreover, let's consider the role of electrical inspections in ensuring proper grounding and bonding practices. Electrical inspections are conducted by qualified electrical inspectors to verify that electrical installations comply with the National Electrical Code and other applicable standards. These inspections play a critical role in identifying and correcting potential electrical hazards, including deficiencies in grounding and bonding systems. During an electrical inspection, the inspector will typically examine the grounding electrode system, the grounding electrode conductor, the equipment grounding conductors, and the bonding connections. They will look for signs of corrosion, damage, or loose connections. They will also verify that the grounding and bonding systems are properly sized and installed in accordance with the National Electrical Code requirements. If the inspector identifies any deficiencies, they will issue a notice of violation, which requires the homeowner or business owner to correct the deficiencies within a specified time frame. A follow-up inspection is then conducted to verify that the corrections have been made. Electrical inspections are typically required for new electrical installations, as well as for renovations and additions to existing electrical systems. They may also be required periodically as part of a routine safety inspection program. Hiring a qualified and licensed electrician to perform electrical work is the best way to ensure that your electrical system complies with the National Electrical Code and is safe to operate. A qualified electrician will be familiar with the National Electrical Code requirements and will be able to properly install and maintain your grounding and bonding systems. In addition to hiring a qualified electrician, it's also important to be aware of the potential electrical hazards in your home or workplace. This includes being aware of the signs of electrical problems such as flickering lights, sparking outlets, and tripped circuit breakers. If you notice any of these signs, you should immediately contact a qualified electrician to investigate the problem. Proper grounding and bonding, combined with regular electrical inspections and awareness of potential electrical hazards, are essential for ensuring electrical safety. By taking these steps, you can help to protect yourself and others from electrical shock and fire.